Yes.
Martin, do we have a note taker for this session?
We do have two new note takers, yes.
Excellent. That means we can start soon. Thank you.
It is 4:30, yes. And since we don't want to run out of time again, we'll start on time. I'll make this very brief. Welcome to the second TSV working group meeting. This is the note. Well, you should have seen this by now. If you haven't, please read it. We have note takers. Again, we need reviewers for working group drafts. And this is our agenda for today. First, Magnus will talk about DTLS protection for SCTP. Then we have 3 talks by Michael and one more talk by Louis. Any agenda bash? Then this is what we are going to do. We'll also try to squeeze in John's talk. Mm-hmm.
Hello, yeah, it's on. Just. Hello, everyone. So I'm Magnus Westlund. I'm representing the other co-authors, John Price Mattsson and Claudio Porfiri. So I'm here to talk about the DTLS security for SCTP. There's 3 different drafts here. So I will get into that more, so please go forward. Slides. So the background here was really about, I mean, it's been a while since 3DPP requested IETF address the message size limitations in RFC 6083, which is DTLS over SCTP. The working group adopted this DTLS over SCTP BIS draft to address this issue. During the fall, we found some security concerns with SCTP auth, as well as realized some erroneous security assumption from our perspective. And where the situation is still, 3DPP still need a solution that support these larger message sizes, meet some modern security requirements, and support long-lived SCTP associations. And to note, there's 2 sets of IPR declarations, both on the DTLS over SCTP and the DTLS in SCTP draft set. So if you can review those. Next slide. So some of the challenges we had with, don't do that. Tell me Techo to adjust it still. So in the development and work with DTLS over SCTP, we had several issues we've seen there. There's high requirements on the DTLS implementations, with several uses that aren't that common. For example, large DTLS record sizes beyond normal IP packet sizes. Also, the usage of DTLS connection IDs. We also had the interesting rekeying interacting with the independent message size fragmentation and their placement in receiver buffers, which requires quite advanced tracking or good APIs into the SCTP stack. And it was also very fragile to errors that could result in SCTP association termination as the only way out of this and restart. And it also provides no encryption protection of SCTP internals. It's only authenticated through SCTP auth. So, and that in itself has some interesting properties too when it comes to replay. We'll maybe come up later, but it's basically saying that those chunks that doesn't have sequence numbers, you can't determine if they're replayed or not if they're coming in an independent packet. We also are dependent on an update of SCTP auth if we're going to keep on using DTLS over SCTP. So as a solution. So let's go to the next slide. So that's another lesson from SCTP auth we have is we feel like from a general security perspective here is that when you embed mechanism that's fairly niche in some sense from an IETF perspective in usage. It's and not that much used. You have a problem that maybe it rots. You don't see when there's security issues, etc. So we really want to look into trying to ensure here with the path forward that we have better way of integrating security protocol that is well known, maintained, and used individually in sufficient numbers, etc., so that any security issues are found, etc. So that's why we try to define a mechanism that uses this protocol as much as this. Basically, just explain how you use the protocol to protect the data we want to protect in SCTP. So that's the basics for this proposal. So next slide. So details in SCTP. So that's the alternative proposal. It's in these two drafts. And we have a very generic chunk, crypto chunk, which uses something we call a protection engine, which is based where we define one for detailless. But you could define other protection engines based on other security mechanism if you want to. And this changes so that it works on applying security protection on chunks in an individual SCTP packet. So it's very similar in that sense from SCTP auth from what it protects, except that we don't have yeah, doesn't matter. So and because it defined multiple protection engine, we also need to specify a little bit about how you can negotiate it, but we'll come to that. So next slide. So the general integration into the stack is trying to be depicted here. So you have a protection engine, which is going to have to deal with packets, protecting them at each one for one. But in the SCTP stack, you have the crypto chunk handler, which basically then calls to the protection and hey, protect or deprotect each packet. And then you have to have some interactions with how you get key management. The current draft set lets the protection engine basically emit crypto chunks on its own. We'll come back to that with some discussion we had on the list and why you might want to change this. But and then you also the applications saying the upper layer protocol here. Also, I mean, is usually in part of saying which identity does this stack have, which crypto, which peer certificates do we accept, and all these aspects. Those still needs to be talked between the ULP and the protection engine. So we can go to the next slide. When it comes to establishing this, you basically do the four-way handshake. And in the initial init, you include a parameter saying on crypto chunk support, and then you list all the protection engines you support. And then the peer responds with the init ACK, indicating which of those it chooses, which is also itself supports. And then you conclude the handshake with the cookie echo cookie ACK. Then you need to establish so that you are protected and ready. So that means running any key management establishment set. And that's why you go into this protection pending state. In this protection pending state, you're still not allowed to send any data for the ULP. And instead, you're just doing handshakes, etc. And when you manage to do the handshake, you go into the protected state. And then you do one more thing here, which is sending what's called a p-valid chunk over the protected channel you established. So basically inside the security, you're sending this. And that lists what protection engine you were offering and support. So that's to ensure that you can't get easy downgrade attacks. So this downgrade protection is as strong as your security, as I say, that you actually established. But it's so if you have really, really weak security mechanism, you could be fooled. But otherwise, this is also been used, for example, in TLS, etc., for similar protection. So next slide. So the details protection engine, this defines how you use the crypto chunk. We basically take the unprotected payloads, which is then it's a set of DTLS of SCTP chunks, and we encrypt them in the DTLS record. We use replay protection, and one effect of this is that the DTLS record sequence number will be a strict SCTP packet transmission sequence order. So as SCTP stack sends packet, that's the sequence number order we'll have, which makes replay, etc., easier to deal with. The DTLS handshake is performed in an initial impact protection pending by having DTLS packetize the DTLS message for handshake into crypto chunks and send them in as SCTP. And in that, the current draft description, it's going to be DTLS that's responsible for retransmission of DTLS messages. This has some interaction with the SCTP multi-homing. So for normal data, this is just handled by SCTP, but for the handshake, we are kind of dependent that your current path works. Otherwise, it would fail. And we didn't maybe thought this through in detail because we've mostly been using a rather short heartbeat interval, no more than 2 seconds, which means that DTLS handshake shouldn't time out. But yeah, so this is one thing we're discussing. I think going forward here, we maybe need to look into more and changing. When you do rekeying, you basically just send during an ongoing session, you just decide, now I want a new DTLS connection, and then you send this as new crypto chunks to the handshake in parallel with the existing session as it continues to work. And when you establish it, you can just switch over to that connection DTLS connection ID as the one that's used for protecting the packet. Then you can just wait a few RTTs, and then you can close down the old one, which is significant improvement compared to the others of what kind of how you handle the switchover. Because if before we DTLS over SCTP, you actually have a challenge there to knowing when they've been delivered. Here you would know that basically a short timer is sufficient to ensure that you don't have a problem. And even if you would drop it a little bit too soon, it would only mean that the packets register as lost and not result in failure as for DTLS over SCTP. Next slide. So this was something Michael Tuxen brought up in discussion about this handshake packets. So an alternative here, which I think we need to think a bit more about, but I want to think it's interesting enough that I want to bring up. But that's basically saying that the handshake message would go through the SCTP stack and be sent in data chunks, while the packet protection would still be on the side between the protection engine and the crypto chunk handler. And the same API between the ULP and the DTLS protection engine would still need to exist when it comes to this basic establishment of certificates on these things. The downside I see is that state management, which was very clear when it was established and you could start sending data, becomes a little bit more complicated with this, because you need to allow the protection engines to send through the stack, but not the ULP. So therefore, you probably want different APIs between the ULP and the SCTP stack and at one, so that you can keep those separated and cleanly. And maybe then also needs to be able to turn off the retransmission details. I'm saying that it should be turned off. That would be probably because you're going to have reliability anyway. But in worst case, you're just transmitting them anyway. You're just wasting bandwidth. They should still work. Next slide. So another of Michael's concerns is about the implementation and the possibility to implement this. It's, yes, the kernel part of this, of how you're dealing with the kernel to DTLS stack interaction is yes, it's not ideal, but it's do simplify. I think it streamlines things, and it does keeping this separation as clean as we think we can get it now. So either you do a kernel to user space call for each packet and get the packet back after you protected it and then continue processing. Or you have to do some embedding or loading of the DTLS record protection or something like that into the kernel. So So basically, you can split your DTLS stack into two parts. One, which is basically crypto processing, and this has been done for TLS. There's TLS and some crypto engines, etc., does this in the lower layers in the kernel space compared to the other, and leaves the handshaking mechanism up in the user land. And from our perspective, we aren't specific about this. Yes, you're going to need to have some of these APIs, which the arrows indicates. But that's not necessarily used that we define them from our perspective. I know that Michael is not maybe sharing that, and he can hopefully speak on that on himself. But yeah, you need to understand what these APIs are. So next slide. Michael, should go ahead.
We can wait until the end.
Well, yeah, okay. So, I mean, I think basically rehashing here. Okay, I can finish up this slide. So, benefits of DTLS in SCTP is really, it encrypts all of the SCTP chunks. You get improved replay protection also of SCTP chunks that doesn't have sequence numbers because of the DTLS replay protection window. The rekeying mechanism is much more robust, and you have less need for tracking things. You use specified DTLS 1.2 and 1.3 as defined, and you can negotiate which of them are. And your DTLS stack dependencies has been significantly reduced. So that's the easiest benefits. So, and basically the question I think for the group is which direction we should go here. If you should go towards DTLS in SCTP and abandon the DTLS over SCTP for now. So Michael.
Yeah, so the main problem I have with this solution is that right now I haven't understood how to implement this in kernels with a kernel implementation in an appropriate way. I'm not saying that you can't. I'm just saying that I don't know yet. I don't see some other things like why do you need a replay protection? SCTP has one, but that's minor things.
Yeah.
You said I have not a problem with doing the encrypt decrypt stuff in the kernel. That's easy to do, but you have to do the managing the crypto parameters which are held in the DTLS implementation, pass them down via socket API. The problem is if you have to pass things up again, you might need to serialize things, and that might be a problem. That's where I'm not sure. It's just not doing the handshake, get down the crypto parameters, and you're done. This helps for sending and receiving until you get pure DTLS messages again. Conceptually, as I said, this looks like running SCTP over DTLS, just with a packet format that not the whole SCTP packet goes into the DTLS payload, but only the list of chunk goes in the SCTP payload. Then you do your DTLS processing, prepend the crypto chunk header, prepend an SCTP commit header. And as I just figured out, there are some limitations, like you can't do restart, and I think you can't do dynamic address reconfiguration. So there are features of SCTP you can't use.
Okay, dynamic address.
If the peer restarts, he has no state anymore. So he sends another handshake message in the established state, and you say in the established state you accept only crypto chunks. And the other one with ASConf is that when you get an ASConf packet, you get a common header, an auth chunk, and an ASConf packet. The ASConf packet contains an IP address. You need to look up the association. So you would need to know this address, look up the association, then you have the key material to decrypt it, and that's too late. So you can't find the association based on the common header.
Yeah, I agree. That's a weakness in that sense. Yes, for ASCOMP. And restart clearly isn't. If you lost the crypto context because of the restart, you're going to have to reestablish it. And I think that has to do with the detailers primarily. If you had something other keying, another protection engine, you had the key somewhere else stored, and you had, because I mean the binding between the initial session is between basically the SSP association has identified a VTag and which set of keys it is based on a counter, which we only send the last 2 bits of. So that identify which keys are used to protect each packet.
Yeah, and you will need to be willing to process chunks which are not crypto chunks in established state.
Yes. So I'm happy to look into more these like ASCOMP and the at least to see what we can do with that. So I mean, we wrote this as saying only crypto chunks because what we really mean there is what's absolutely necessary is things that either affects the association in a really bad way or can take it down, as well as the data. So I think, yes, we can look into some exceptions there for what's really necessary. But it needs to be saying, it's going to be a trade-off there saying, is this acceptable from a security point of view? That's, I think, is the consideration there.
Yeah, but my main concern is about the architecture. So I right now don't see how to implement this in kernel space.
So we have Martin Duke also.
But you can say you don't. Yeah, but you can say you don't. It's not important for you, and then that argument goes away.
Yeah. So Martin, what's your?
Hey Magnus. So I guess I don't understand what you're proposing. Do you want to abandon the existing DTLS over SCTP BIS draft and replace it with this? Or
yes.
Or not? Okay.
Exactly.
And do our friends at 3GPP have a position on that, or do they care as long as we deliver DTLS over SCTP to solve those problems?
I had done some work on trying to get the feedback from them. So far, I hope that maybe someone can comment on this further where they are on this. But so far, it seems to be. So I hope that we will see some feedback from a few at least. So.
Okay, thank you.
So, Charles?
Yeah, Charles Eckel. So I think you did, so we're taking care of the liaison statement that kind of fell on the floor before, and that will provide, that'll be looked at the April meeting, so we'll make sure that's on the agenda and we'll get something at that point. Yeah,
I hope that for SF3 and round 3 already been informed. I was hoping that some of the people would react that in their latest meeting a few weeks back. So I was hoping. No, that one a couple meeting, just it was the week before last. That was the plenary meeting, and they didn't really talk about. They didn't bring it up fully. But it's at least I tried to reach out to the on the mailing list at least to say, hey, we have this thing coming up. So, but yeah, okay. So, but yes, I really, really would appreciate some indication from other people active in 3DPP about that actually have products in this side to chime in on this, because it's. I think we need to make a choice rather soon, but I think we can leave this on for mailing discussion for a while more when we will consider some of this discussion and feedback we got. So. Corey?
I wondered if I could ask if anyone else has passed comments or read these particular proposals that we've seen presented today. Did you have any feedback, Magnus? Does anybody in the working group want to also comment? First, Magnus. Magnus, have other people apart from Michael commented on this?
No, not yet. I met some person from Nokia that would try to take a look, I think, on, but haven't received anything yet, but I hope for. So.
Yeah, thanks for presenting it. And I guess a question generally to the room, is there anyone in the room who wants to make a comment here? Michael, yeah, go ahead. Anyone else, please join the line because we need to move on in a minute.
Yeah, so just one comment. I don't think the Linux kernel SCTP guys are on this list. So we can reach out to them. Not sure. In the past, they participated in testing, but only limited in standards development.
Yeah, please do. Okay, and once we understand which way you're proposing we should really go, I think we probably will need to make some working group decisions about the direction of the working group work item for that.
Yeah. No, so I mean, I think we will, let's discuss for a while and then let's see how it goes and then decide on doing a consensus call or something on the mailing list for which direction.
Sounds like a good plan. Thanks ever so much for your talk and for the pictures as well. Good to have pictures when we have discussed these things.
Thank you, Magnus. And we'll move on to Michael's presentations.
Can you run the slides?
Yep.
Okay, so this is the first presentation. It's about a very simple feature, zero checksum for SCTP. Next slide. So the modification, so the context is SCTP used in WebRTC, which means you run SCTP over DTLS over UDP. This is implemented in browsers and it's used. And the problem I want to address is that the checksum computation, the CRC32C in SCTP is CPU intensive. And when running SCTP over DTLS provides no use because the DTLS layer provides much stronger protection. So for saving CPU cycles on the one side and helping DTLS implementations on devices which have limited CPU resources, the idea is to just get rid of computing the checksum in a backwards compatible way. So I'm aware of some DTLS implementations on, not DTLS, data channel implementations on IoT devices, which just don't compute the CRC on the receive side, which is something they can do without breaking the interoperability, but this is for sending and receiving. Next slide. And this is an example how this works. If you use the socket API, you basically see that in the handshake, you have an additional parameter support zero checksum acceptable, which means that the endpoint sending this init or init adjunct is willing to accept packets without a checksum. This, for example, means that the init ACK can already use 0 as a checksum value. You also see here that the cookie echo is a special case because when you receive the cookie echo, you have no association context at that moment when you start processing because you establish that association with this packet. And this packet also needs correct CRC32C, like the packet containing the init, to be backwards compatible. So for the init, it's for backwards compatibility. For the cookie echo, it's for ease of implementation. All the other packets, as you can see here, can have 0 checksum. Next slide. So what has changed since the last version of the document? We got some comments from Claudio, Gori, Magnus, and Mike. Some of them were in this, were based on a misunderstanding that the sender could make a choice. This packet is important to me. I put in a CRC. This packet is not important. This is not the intention. This is about saving CPU cycles when the whole computation does not provide additional value. That has been clarified. Also has been clarified that using SCP authentication doesn't help because the header is not protected. We added text that cookie echo chunks and packets containing cookie echo chunks and ASConf chunks must contain correct CRC32C, because when receiving the packet, it's not, you with the first lookup of the association, you don't find it normally. So it helps simplifying the implementation and to allow out of the blue packets with incorrect zero checksum. If one side loses the context, you can clean up in a fast way. Next slide. So the implementation status is that it's implemented in the FreeBSD kernel and in the userland stack, user SCTP, which is based on the same source code. And it's basically under review for DC SCTP, which is the data channel SCTP implementation used by Google for their browser. And you have a test suite for this stuff at the URL I provided, and I showed one of the examples. Next slide. So from the perspective of the authors, the document contains everything which is needed. We have 2 implementations. So it would be interesting to know what the working group thinks should be done to get working group adoption. And of course, we would address all these comments and any additional feedback. That's it, I think, from my slide. I guess that's the last slide.
Are there any comments from anyone in the room?
Martin is in the queue.
Hey, Michael, I've not read the draft. I'm curious, do we have any data on how serious a problem the CRC32 is? Or, I mean, like, is it a measurable, are you just cleaning up like unneeded stuff, or is there like a measurable effect on CPU load of this protocol?
It is measurable. I did some measurements only with SCTP in my lab. It can go up to 1/3 of the CPU you need to process SCTP packets. That's only for SCTP, so people use DTLS and whatever, but I'm aware of people running WebRTC data channels on small devices, and they disabled the checksum computation on the receive side to get a substantial improvement on what they can handle. So yes, it is important. That's why we are bringing it up here. If you're in kernel space, there are Intel NICs which do the offloading, and you have some CPUs with specific, so you can do other things, but this is something hard to do in userland.
Thank you.
Quick show of hands. Who has read this draft? Okay, that's 2 people in the room. Shall we make an adoption call?
Anyone has to go on the list.
Yeah, let's do a quick adoption call. So please use the Meet Echo tool and raise your hand if you think that the working group should adopt this draft.
After the adoption call, we'll ask if people wish to give any reasons for not progressing with the work or concerns they have. So please be ready for that if you have concerns.
So that's 14 votes so far, all of them in favor of adopting this work. And as always, we'll confirm this on the list.
Okay, so I think we will ask on the list for more feedback to see if anyone has concerns or issues and whether we can adopt this item. Thank you, Michael.
Thank you. So Gori asked to give a 45-second overview of the other 2 things to save some time. SCTP authentication, if you go to the next slide, yeah, that's basically the motivation. And I haven't done anything except for changing the document. So I started with, what is it, RFC 4895, submitted the document, converted to XML v3, did some editorial things, and didn't do any substantial work on it. This will be done next, which basically means integrating or fixing the issues brought up by Ericsson recently at Socket API considerations for dealing with multiple algorithms. This is something required for DTLS over SCTP, add some more algorithms, and there was some years ago a document which raised some issues about wording, which also will be integrated. Nothing of this has been done, but I'm planning to do this for the next IETF. And if you have comments, suggestions, you can bring that up on the mailing list or send me an email. You can go to the next slide deck. You just can finish this and go through the UDP and CAPS thing. Oh, Magnus comes up.
Yeah, I just want to point out that, I mean, we are very dependent on this SCTP auth if you're not moving to the other details in SCTP's solution, and especially the new algorithms that will be direction dependent handling of the authentication. So
yeah, I'm aware of that, and I just wanted to clean up other things. So but even if the working group decides not to do DTLS over SCTP but go with another solution, I think the issues should be fixed, because SCTP authentication is still needed for ASConf, and so there is no argument whether this should be fixed. The priority for the decision of the priority in the working group might depend, no, not might, depends on the decision with your documents.
Yeah, okay, good.
Okay, can you go to the next slide deck, Martin? So that's SCTP over UDP. If you go to the next slide, so this is basically about doing a BIS for RFC 6951, where some text was submitted, and the missing text is in the draft there, and it was suggested by I think it was Magnus when he was still at Transport AD, and by the current Transport AD Martin, that not have two documents for SCTP over UDP, but a single one. So this is basically integrating this into a BIS document, and it might need some wordsmithing, but it's done. How we put this into the priority on the working group depends on, I guess, how important SCTP auth is. For me, it's just important that the document is there and people implementing this know this. It is implementation status. It's implemented in FreeBSD. It's implemented in Linux with the fixes. So the kernel stacks have that. Questions, comments?
So this is super short.
Yes.
It's not a document. It's probably one that many people could read. So I'd be interested in hearing from people. And maybe even we should start a question about how many people think they will review this. Because if we have people to review this, then I think the pathway forward will be much easier.
So I'm happy in any feedback I get, of course.
So Martin, can we organise a quick show of people who are willing to review this, either by raising a hand or doing a poll? Yeah.
Show of hands. Who would you review this document? Or put it in the chat if you're not here.
Please raise your hand in the room if you would like, or if you would be willing to review the document, or indicate in the chat. Magnus is raising his hand.
And Claudia on chat.
Gary, do you want to go for a online vote to see who actually thinks that we should work on this topic, or who thinks this area is important to work on?
Yeah, I would like to get more sense of what people think, because it looks easy to do. It's a simple document. So yeah, can we do an online poll of who thinks this is an important document to produce from the working group? In other words, should we put energy into producing it at the moment? Okay, so I saw 8 responses and I didn't see 8 hands, and the document's quite short. So I think what we need to do now is get a few more people to volunteer to review, and we'll talk with the document editors about whether we should start an adoption call for this item. Any questions from Michael? Are you clear?
No, I'm clear. Thank you.
We have a plan.
Then we'll move on to Lewis's presentation.
Yeah, I actually tried to in the screen. I mean, in front of them actually. I know that
you can get the control on your phone if you log into the on-site tool. Next time.
But this time, actually, just for the sake of the people in the room, actually, right? I think I just used this.
You can take the microphone off if you want.
I think it's okay. My name is Louis Chen. I'm going to present a solutions, which for the CGNet. So it's a kind of features missing today. Still, although we have IPv6, the CGNet IETF is being used by a lot of population in Asia, but especially half of the Asia consume the CGNet. So over terabits of CGNet is being sold in the last 2 years. So there's still a lot of populations running under a shared IP because we lack of IP. So for the mobile, I think there's no problem. For CGNet, I think that's okay because they don't need some kind of services, mostly for the cloud. But for fixed line, if they want to compare to today with a pure public IPv4, it's different, the service. But people do not know. They just need, okay, I need a real public IP address to solve the trouble. So therefore, this draft is enhancing the experience, user experience from the application perspective, and how that one's the kind of service can enhance from the user experience perspective. Next slide, please. The problem actually is, today, there is kind of under the NAT444, that means with CGNet, if you want to do some P2P connections, that means your voice or kind of games, whatever, you need to punch hole. By RFC 5128, you can do hole punching. But there is 2 requirements. First of all, you need a kind of third-party server, a common third-party server to signal the 2 sides. And if the 2 sides at the same time to synchronously do the same thing, that means if the UDP timeout is 120 seconds, within that window, they need to shoot the packet to each other at the same time. If you miss that window, the connection will fail. So you need to coordinate that at the same time. So it's really difficult to TCP to work because you already passed through two kind of NAT. And TCP sync is very complicated, right? You know that. So therefore, TCP normally doesn't work. Only UDP will work actually. So this is why you see that a lot of the voice, whatever, they transmit using UDP to punch it through. So the solution right now is missing is how to make it work under these are NAT 444 situations. And then this kind of the solution I'm going to pose is something I need to work on the kind of CGNet, and the kind of method will be allowing not only UDP and also TCP can be run asynchronously. That means you reserve the port, just like you do port forwarding at your home gateway. I think people use a home gateway Wi-Fi router, you know port forwarding, right? The experience is the same. I mean, allow the CGNet user, I mean, behind the scene, they still can use this kind of service. I mean, I have a port, then you can host some service like HTTP, SSH, whatever, okay, or behind the CPE device, although under CGNet, okay, which is not possible today. Today, all the TCP, once you go to the CGNet, when incoming directions, it will all drop it because it only allow outgoing directions. It do not allow incoming directions. Okay, so this solution is to how to do this asynchronously. That means you don't need to synchronize. You don't need common third-party servers. You can do it asynchronously, and it's just like port forwarding as what you do today. And you need a function called IETF, which I'm going to explain what is it. So this is a lot of words, but the one thing actually is about this one is today do not allow kind of, I mean, most of CGNet do not allow incoming services. It just drop the packets. So we want to have some kind of just like port forwarding function so that when, for example, 102.24 this port will go to the CGNet and CGNet will pass over to the home gateway or the RG or residential gateway RG and then pass it to the PC, your PC, which hosting the service for that one. So we want to punch a hole. At the same time, there's only one will receive this port. That means along the chain, only one, for example, 102.24, as I say, along the chain, only will have one device behind the home gateway or the RG residential gateway to receive these traffics. So we make sure that there's only a kind of a unity actually in this version. But there are some consideration. I'm not going to explain this one in this slide because it's a bit complicated. I will let it over after the demonstration. I'll give a demonstration first, and you understand how it works, and it'll be simpler. Next slide, please. This is a demonstration, okay? Here, there's a CGNet here. Actually, I use my home kind of a router to simulate this one. You know DDWRT are open source, right? Then I use DDWRT to actually chain two devices. One is a simulation of CGNet. The other one is simulation of RG. Okay, the CGNet with a function turned on called IETF, which is if this is off, every packet in the incoming direction from the internet will be all dropped, wherever traffic, unless the section table is built. Otherwise, you drop it. But if the function is on, which I need this function, which is stateless actually, no state, stateless, right? Then this one will allow some port to be passing through under some conditions, right? And then here, there's a new procedure. In order to get this one is a stun procedure. And then I will use some procedure here to demonstrate how it works in this case. So you look at the IP address, okay, just very simple one. From the left side is the 160.20.100, and then 20.1, 1.11, which is the WAN gateway, WAN address for the RG, which is home gateway, and then the CGNet, and then CGNet, there's a public IP address, okay, which I mentioned here, but the port allocated to this particular native IP address is 1024 to 1055. The port range are allocated for that one. That means there's one port range where we stick to one private address which allocated to the home gateway. This is called port allocations. Okay, but in some cases you only have one port maybe because of depending on implementations, right? Sometimes it's a range of the port. Sometimes it's only one or two ports, right? But anyway, this method will work for either case. But here, just an example saying that how it works, okay? It will just allocate a range. That means whenever traffic going out, it will select randomly which port is going out from this range, 1024 to 1055 as the source port. As a source port. When it's just CGNet, right? Whenever mapping, it just go like that way. So there will be, in the example, it will be a kind of a traffic which randomly, in the example, it will be 1035 is coming back. So I will illustrate how it works in this case. First of all, the PC1 in this diagram, the left-hand side of this diagram, will use a stun kind of procedures. What it does is just detect what is my public IP address, what kind of port I'm using right now from the CGNet perspective. So randomly, because this time is random, right, between this range, 1035 in this example is being detected. 1035 is available, okay, I'm using. Then what the RG is doing, the PC is doing, second step is I send a UPnP to reserve the port in the home gateway. Tell that if you see 1035, this port, send it to me. Okay? Then now the TPC services allow. So the tricks with this EIPF on is whenever traffic sending from the internet, from PC2 or PC from internet, this side, on the right-hand side, if you send a traffic with this public IP address and port 1035, this CGNet will see, okay, this function is on. I will pass the traffic unmodified, the port 1035, and direct it to the home gateway, RG, or the resident gateway. And because 1035 using UPnP already registered, it will again forward to PC1. See, it's just chain of forwarding the port. I mean, you understand, right? Just chain of forwarding the port one by one to the destinations. In this case, it's very simple because the benefit of this one, there's no control plane in CGNet. Compared to PCP data protocol, you always have control plane, request and something like that. This is not scalable. This one actually depends on how you write the software, the stun, and then actually detect your ports. That's it. So this is scalable solution compared to the other core PCP solutions. Next slide, please. So this is a quick demo on how it works. Actually, I create this demo, and then there's a video record as well, but without scripts. But here it's very simple. I want a scripts here in the step one. It execute a stun process, which detect my public IP address, and then the port. The public IP address is beginning with 59, if I'm not wrong, 59. 58, right? 58, actually. But the port number is detected, is 1035. And then, secondly, the second step in this demo is it will request the home gateway, the RG, the port mapping, TCP 1035 to me. And then it starts the service. In this same server, this Linux server, I will actually register this port 1035 as a HTTP server. Okay, I host an HTTP server inside here. And at the same time, I redirect the service using UPnP to ask RG to map the SSH to this PC as well. So this is done. Then next slide, please. Then using the address, just provide that one, the IP address and the port number. You just type it in the web browser, it works. It is not port 80, it's not 443. It's a number, 1035, but it will work actually. Okay, the host of service is TCP, this is. Second slide. Next slide, please. Right. And then if you put in the kind of SSH, right? SSH with this port number 1037, another port, not the 35. This is there's another port in the script I reserved. 1037 is direct SSH. Now I'm using another PC, try to access this, this public IP address, and then this port. It will actually get through the SSH. Now this is all asynchronous. This service is similar to what people expecting today using normal UPnP with a public IP address. Okay, next slide, please. Okay, this is the kind of the RG UPnP tables. You see there's a conversion, right? In the top, I highlight in the red box, how the port being translated, okay? 1035 becoming a local ports, actually. Okay. Next slide. So this is the last slide explaining about why I need to check. For example, if the public IP address 1024 is mapped to, owned by the CGNet, and the CGNet will pass it to the RG, and it passes to PC1, in this example, 1024, this port. It's being like this chain, port forward one by one to that one. But this port 1024 is not only used by PC1 behind the home gateway, the RG resident gateway. It's not used by them, only by one PC. Any sections, actually PC1A, PC1B, behind the home gateway, the RG, they still can share the same port, but outgoing connections. There's a chance the 1024 this port is used for other sections as well. Right? This is possible because CGNet will actually just map it, right? So this is not dedicated for PC1. So therefore, it will has a kind of table created for that one. And then actually, I don't want to detail this one, but the essence of this one is when CGNet see the packet incoming, it need to check whether there's an existing session table or not being created based on, that kind of port number. If it is, honor this one first. Okay, if there's checking this table afterwards, there's nothing, no sessions actually inside here. It's a new IP address port, right? Kind of combinations. Then grant the sections and then port forward this one to 1024 to the PC1. To the RG in this case, right? To the RG, not to PC1. To the RG, and that RG decide which PC to send the port. So this is the only checking here. So I think I'm running over a bit of time, but this is my last slide. Any questions? I think it's clear, right? Sorry for the
I think I'd say thank you ever so much for the example work through. That's so helpful. I suggest we take questions on the list, and people can even review your talk here with the example to see what they think about this piece of work and whether they think this is something useful to contribute to. So please take the question to the list.
Yes.
Okay, thank you very much for the presentation. And then we have a few minutes left for John. We are still trying to figure out how to get your slides on the screen, but maybe you can start talking already.
So let me give you the title of the presentation. This was scheduled for the previous session. It's media header extensions for wireless networks. So while we're bringing up the slide, I'll talk through the problem statement itself. So essentially, many media applications require both low latency and high throughput. And wireless networks, on the other hand, experience transient channel quality drops, sometimes in the order of 5 to 10 times. So when there is this huge drop of bandwidth, what happens is that there are queue buildups, and it can essentially drop either in the tail or the head or whatever, depending on what the scheduler uses. But essentially, those kind of drops will result in poor quality for media because maybe it's a few packets of the iframe and so on, So this is the problem that is trying to solve here. So what we think is that L4S and the whole end-to-end congestion control can manage rate adjustment over the long term, but for these very sharp drops and transient drops over a very short time needs another mechanism where the network gets involved, or we need a shorter congestion control loop, which is not so practical. So this has been studied by 3GPP, and when there is RTP, they have proposed solutions where they read the header and then use that metadata to prioritize what to send and what to drop. For encrypted packets, there needs to be some method that I think will need the IETF's help. So it's very similar to what they're doing for RTP, but for encrypted packets, there is no meta header that can be read. I mean, no header that can be read. There are a few proposals in 3GPP which looks at extending GTP, which is not such a good idea, and a few others, but I think the solution should come in this space in the IETF. So our draft proposes, to basically give a few metadata. So one or two of those are the priority or importance, and the other one is a burst length. Using the priority, the scheduler and the radio side can determine which group of packets to drop so that it doesn't indiscriminately drop, important packets or part of a frame and part of another frame and so on. And, so we propose a UDP option to be able to handle this. So basically the importance and a burst length can also help if it's given ahead of time. The burst length can help the scheduler to reserve bandwidth and resources for that expected media set. So that's the idea. It's a little bit hard to explain, I think, but please have a look at the draft. We're open to suggestions on other solutions. I think this is a space that is preferable that the IETF proposes a solution or gives some feedback on that rather than, because it's something that the IETF should and not 3GPP that should be working on this. So please have a look at the draft and I'd appreciate feedback, suggestions, and whether this should be done one way or another. Thanks.
Thank you, John. And sorry we didn't manage to get your slides up. They were not available on the data tracker, and then we tried to screen share, and then the network cut out.
That's okay. I hope I'm able to convey the problem, and I hope I can get some feedback. Thank you.
So that's it for today. Thank you, everyone.
Yeah, thanks everyone. Cisco.